This presentation is about kinetics. It's actually one of the more interesting areas of chemistry, and unfortunately we don't have much time to spend on this, so we'll just kind of give you kind of a brief walking tour, maybe an overview of what kinetics is all about. So one of the reasons why we should study kinetics, we want to know how fast a reaction is going to happen and what factors control that rate of reaction. So chemical engineers spend a lot of time dealing with this. Actually, people that go into health-related careers often deal with this in one way or another, whether they realize it or not. There's a whole field of pharmacokinetics. So there are pharmacokinetics here as well. And quite often when in a hospital they're monitoring your intake and output, sometimes they're also looking at how fast your body is eliminating medicines that you're taking. So they need to know that in order to know when the next dose can happen. So people involved in health careers often indirectly or even directly deal with kinetics. And aside from making observations about the amount of time it takes, we also want to express these relationships mathematically. And we won't spend a lot of time dealing with the mathematics here, just kind of getting a general feeling of this. And then people even want to burrow deeper, and they want to know on the microscopic level what's happening during a chemical reaction. How are bonds breaking and how are they reforming? And that is called I've got kind of clicked through this. I forgot I had some things. So how fast a reaction happens is called a reaction rate. Rate laws are the mathematical expressions used to express how concentration affects the rate of reaction, and the Arrhenius equation expresses how temperature affects rates of reaction. And then a mechanism is kind of a cartoon-like drawing that we put together to explain how bonds are breaking and forming. But anyways, one of the basic theories of kinetics is called collision theory. And this whole premise here is that in order for two molecules to react with one another, they need to collide. And not only do they need to collide with sufficient energy to break bonds and reform bonds. There's also an element of orientation. So even though two molecules may bump into one another with sufficient speed or kinetic energy, they may not be oriented right to break and form bonds. So not all collisions are effective. And one of my kind of mental models of the collision theory is demolition derby. There are some elements I'll try to point out here during the next few slides. Okay, well, I thought I had another slide on another kind of pop in here, but I guess I don't. But you would expect the one with the greater number of cars to have a greater number of collisions. So that's the whole premise here. So likewise, when I have molecules or atoms instead of cars, the container with more molecules in it is more likely to experience more frequent collisions, and the more frequent the collisions, the more likely a collision is to produce a positive chemical reaction. So increased concentration leads to more frequent collisions, and if we have more frequent collisions, we're going to have a greater rate of reaction. So the greater the concentration, the greater the rate of reaction. And then temperature. So I've got the same number of molecules in two containers. One's at 20 degrees Celsius and one's at 100 degrees Celsius. And if you remember from the previous unit, we talked about the kinetic molecular theory of gases. And one of the premises was that the kinetic energy of gases, or the speed at which they're moving, is only affected by the temperature. So the greater the temperature, the greater speed they have. And you can expect that with more speed, we're going to have more frequent collisions. And if you have more frequent collisions, then you're going to have a greater chance of having a reaction. Not only that, but since they're at a greater energy, they're more likely to break and reform bonds than at a lower energy. Okay, here's a joke for you to ponder. Should be part of the Iowa graduation standards. Any ideas what this is? Hold on to your hats here. It's a catalyst, which is not, actually what we're going to deal with here. So seriously. In reaction profile, we have our reactants and products, and it's not just a downhill slide between reactants and products. We quite often have a barrier between them, so I can mix my reactants with one another, and quite often they don't even begin to react because there's not sufficient energy to propel that reaction forward. So I've got a little hill there, and I can do things like increase the temperature. So if I wanted to get this reaction going, I could increase the temperature, giving the reactants enough kinetic energy to get over that barrier. So that's what we can do. Or if I've added a catalyst basically decreases that energy barrier. So now more particles will have enough energy to get over that barrier and produce products. So if the barrier is lower, I'm going to have more molecules with sufficient energy to get over that barrier, so the rate is going to go up in the presence of catalyst. Some examples of catalyzed processes. Your car probably, hopefully, has a catalytic converter, and it catalyzes the reaction between oxygen and other gases in the atmosphere to produce less harmful emissions from your car. So if your catalytic converter is operating the way it should, then it has a lower amount of things like carbon monoxide and nitrogen oxides being emitted from the end of your tailpipe. Most biological processes are catalyzed by enzymes. So these enzymes do a variety of useful things in metabolic processes that include the Krebs cycle, glycolysis, and all sorts of things. But I just kind of picked out here that pepsin is an enzyme found in our digestive tract that helps break down proteins into smaller chunks like amino acids. Yeast, among other things, has an enzyme called catalase that can break down hydrogen peroxide. Chlorine radicals, if they get into the atmosphere from things like CFCs that we use in things like air conditioning and expanding, styrofoam foams and things like that, they get up into the atmosphere. Ultraviolet light breaks them down, producing these chlorine atoms that have an unpaired electron, and that unpaired electron is very reactive and can react with ozone to break it down into just plain old O2 rather than O3.